Right, welcome Math students. We're going to start a new section today on vectors. This is chapter 8 in your textbook. So the first question we're going to answer is, what is a vector? Well, a vector is a quantity that we measure that has two components to it. It has something called magnitude or size, and it has a second part to it called direction. Now let me explain. If I said to you, let's count out 20 marbles. Okay, you'd take a marble can full of marbles and you'd count out 20. You wouldn't need to know anything more because you just need to know what 20 marbles look like, and you pick them out and there's your 20. We call that a scalar quantity, a quantity with only one component to it. Okay, by telling me that there are 20 marbles, you've told me enough information. But if I said to you, walk 20 kilometers, you might look at me and say, okay, but where? Or which direction? You see, you'd want to know a little bit more, because 20 kilometers, if I walk it one way or another way, I'll end up in a completely different place. So to really get to where I should go to, I need to know not just how far to walk, but also in which direction to walk. And so when I say 20 kilometers and I give you a direction with that and say something like 20 kilometers north or 20 kilometers in the direction of that tower, okay, I'm giving you two parts of information, and that means I'm giving you a vector quantity. All vector quantities are also dependent on direction. So we're going to see how that affects some of the mathematics involved with what we're doing. So I'm going to show you some interesting things with regards to vectors. Okay, so that's the first thing you need to know about a vector, is that it has magnitude and direction. Okay, now secondly, how do we represent vectors? Well, one of the simplest way is to put a point A and a point B and to join a line between them. Okay, and we normally put an arrow on the direction that we want to go. So if we said go from A to B, then you could follow in the direction of that arrow. Now, one of the interesting things, and I'm going to actually use the textbook to show you this, if you have a look here, okay, they represent some vectors here. You can see the A to B vector on the diagram, but you can also see a vector that goes from R to R prime, from Q to Q prime, and from P to P prime. All of those points are on a little disk or flat disk of board, okay, and both are identical on either side, and they match points up, equivalent points on either side of the board. Okay, notice that A and B, or A to B, and R to R prime, and Q to Q prime, and P to P prime are all vectors that move in the same direction and also have the same size. Now, that doesn't mean that they go from one same point to another same point. You can see that they go from different points to different points, and yet the vectors themselves are the same size and the same direction. So we would say that these vectors are equivalent to each other. Okay, they are equivalent to each other because they move in the same direction and they have the same size. So here you can see on the next page they say that AB is equal to P prime and is equal to Q prime and is equal to R prime. And the arrowheads show that there is a sense of direction. AB is drawn to scale, and to give the correct magnitude of the displacement. And then we can also label these vectors as AB or PP prime. So one of the ways we now write vectors is we say that a vector is labeled like this. Okay, AB with a little arrow on the top. Okay, or if you wanted one of those other ones, PP prime with an arrow. That indicates that we have a vector, which means we're going from a point A to a point B, or from a point P to a point P prime. Okay, in whatever direction. These are just labels that we're going to be using. Okay, now they talk about the equality of the vectors here, and you can see they've labeled 3 of them: A, B, C, D, and E, F. And because these lines are drawn to scale and they all go in the same direction, we would say that they are equal to each other. Okay. So what this means is that it says if AB is equal to CD, then the line segment AB and CD are equal in length, and also that AB is parallel to CD because it is in the same direction. We could also say that CD is parallel to EF. Okay, now look there, they've drawn you two vectors, AB and CD, equal in length and also parallel to each other. This means that that figure ABCD must be a parallelogram, because if you remember, some of the requirements for parallelograms are that there must be at least one pair of opposite sides that are equal in length and parallel to each other. That is enough information to prove a parallelogram. So here we're just talking in terms of a vector, okay? And so AB being parallel to CD as well as equal in length would form a parallelogram, and we've got that the AB vector is equal to the CD vector. Now, something else we can do is that we can label a vector as follows, okay? We've labeled it AB with an arrow, but we can call this AB vector just vector A. So very often you'll see like a bold printed A in a textbook, okay? And that would normally indicate that that is a vector. So if we called vector A, it is the vector from the point A to the point B, okay, with an arrow on top, okay? So one of the things that just sometimes that we'll use is just a label for a vector. This is going to be important in a moment. You'll see as we use this. So now we're going to talk about the magnitude of a vector, okay? All right, so the magnitude just refers to the size of the vector, okay? Another word that they often use, and don't confuse this word, even though it's the same word that you've seen before, with when we used the word modulus, we meant positive. Now, in vectors, we also talk about magnitude being a modulus because it is really a positive value. You see, you can't get a negative size. There's no such thing. You can talk about things being negative numbers, but the size is still a value that is a positive, okay? The word modulus in vectors also refers to the magnitude or the size of the vector. And we label this with that modulus sign that we used before, okay? So if we write AB, what we're saying is we just want to know what is the size of the vector from A to B. Now again, just talking about something that I mentioned earlier, if I said to you go 20 kilometers north and I said, how far are you walking, okay? Then you would say to me, I'm walking 20 kilometers. You see, that's the size. You wouldn't be saying maybe that I'm walking north, okay, because that would be the direction. But if I just wanted to know the magnitude of how far you're going, it's 20 kilometers. There's the size. So that's the modulus value that I'm after, okay? All right, so it says here, if AB in the figure is drawn to scale of 1 centimeter is 10 meters per second, then the AB would be 30 meters per second if you measured that line, because it is 3 centimeters in length. Okay, you can just trust me on that. You don't need to go and use the ruler. All right, the magnitude of that vector would then just be as denoted as the magnitude of A with the two lines, or just simply as A, and that would simply be a value of 30. Now, just to add to this, we can also talk about a zero vector having a zero size, no magnitude, okay? And of course, if something's got no magnitude, it's also got no direction. And then we can talk about a scalar multiple of a vector. So look at these vectors that they've drawn over here. Okay, we've got the RS vector, the QP vector or PQ vector, and a vector A. Okay, now the vector A that they labeled there, you can see is a certain size. The PQ vector is double the size. So that would then be equivalent to 2A. In other words, 2 sizes of A. And that would mean a scalar multiple, because the number 2 is now a scalar. It's just a value. Okay, and it's going in the same direction as the vector A. So it's 2 times as same as vector A. If I look at the vector TU on the left-hand side down the bottom there, that is half the length of the vector A. So that would simply be also a vector called half A. And then I look at the RS vector, which you can see runs in the opposite direction to the A vector or the PQ vector. So being the same size as the A vector, the R is the same size as A, but running in the opposite direction, we'll call that negative A. So a negative in front of a vector means that we're going in the opposite direction. So let's just have a look here quickly. Okay, so if I draw you a vector now, and I say here's a vector, we'll call this vector B. And then I draw you another vector, and this one's double in length. That vector must then be called 2B. But then I say, all right, I'm going to draw another vector that's exactly the same as that 2B, but it goes in the opposite direction. Well, then that would be a minus 2B vector. So these values in front, okay, are called scalar quantities, and they are multiples. They are multiplied to the vector, okay. So they multiply to a vector, and then they indicate a vector of either double or triple, whatever value we put in front of those. Right, so let's move a little bit further and see what else we've got here. So in example 1, they say that if we're given a vector A, draw the vector 3A and draw the vector minus a third A. So there's the vector A on the left-hand side. 3A would simply be a vector 3 times as long. You can see they drew it there. Minus a third A would be a vector that's 1/3 the length of A, but goes in the opposite direction. And you can see the arrows pointing on the opposite side. That's not too difficult, I don't think. Let's have a look here and see what they've written here. They say, what type of quad would we have if ABCD is given by a vector AB, which is equal to the vector DC? Remember, AB is equal to DC means that a vector that goes from point A to B must be the same as a vector that goes from point D to C. Now, you could possibly say that we could have had a square, but at the very least we would have, if we have two vectors that are different in the same direction and are parallel and equal in length to each other, the minimum shape that we would have is a parallelogram. But look at the second one, which is that AB is 3 times DC. So the AB vector is triple the length. Okay, well, that means it's got to be parallel because the directions must be the same, but the magnitudes aren't the same. And that would indicate that the shape ABCD there would be a parallelogram, a trapezium. Okay, if we had a vector that did that. All right, so here's exercise 8.1 already, and that's with that information you should already be able to answer a few things. So number 1 gives you a vector A and then asks you to draw a couple of other vectors from it. Okay. Number 2 says that you must state each of the PQR vectors in the form of KA. So what you'll actually have to go and do there is go and measure them, okay, in terms of A. Okay. So look at P, well, I'm just going to hazard a guess, but P definitely looks about double the length of A. So that would be 2P, but it also goes in the opposite direction. So that would be minus 2P. And you should do the same for Q and for R and see what you can do there with those. Okay, I'm going to look at number 4. Number 4 says that we have a regular hexagon. Regular means that all the sides are the same length. We're given that the vector AB is given as an A. The vector B from B to C is called B, and the vector CD is called C. Now notice that these vectors might be the same magnitude, but they are different directions. Okay, and so therefore they are not the same vectors. They might have the same size, but they do not have the same direction. So they've labeled them A, B, and C. Now they ask us to name the following vectors in terms of those A, B's, or C. We'll look at the vector DE. DE is parallel to AB, but runs in the opposite direction to AB. So DE would be the same as vector A, but in the negative direction. So that would be a negative A. EF, however, looks the same as the vector BC, also runs in the opposite direction. So EF would then be minus B. And F to A similarly would then be minus C. But now what about the vector BE? Well, from B to E, okay, I'm not just going to be able to see what that is, because I don't really know what the length from B to E is. Let's go and draw it quickly on the screen and see, okay? We've got AB, BC, sorry, AB to C to D. to E to F and back down to A. So here's B and here's E. Now, it definitely looks like it's parallel to this vector, but again, I don't know this length, okay? So I couldn't tell you what the multiple is, okay, of that C vector. Remember, this was A, B, C, D, and F, and this vector was vector A, this is vector B, that's vector C. So like I say, this must be some multiple of C, okay? Well, the thing is, okay, and remember that I had D to E was minus A, and then I also had E to F here, if I'm going in that direction, was minus B, and lastly in this direction from F to A was minus C, okay? So is there another way that I can get from B to E, okay? Well, I could go from B to C, then go from C to D, then go from D to E, and I'd end up at E, okay? So going from B to E, I could follow a path of vectors that I already know. So one of the things we can say is that from B to E, that vector, is the same as going from B to C, and then from C to D, and then from D to E. And we know that each of those vectors were already given to us. Okay, so these are not vectors now that we have to go and work out. We already have them. Okay, so I'm going to replace B to C with simply the vector B. And C to D with the vector C. And lastly, D to E, which was minus A. So B plus C minus A would represent the B to E vector. Okay, now you might say, well, that doesn't give me a multiple of the other one, but it does give me an answer for the solution of that vector. Okay, and they said we could use as scalar multiples of A, B, or C in this case. Okay, one of the other things we could go and do is go and work out maybe what this hexagon would do. And let me go and show again on the pictures here. Remember, a hexagon is regular, okay? That means that all the sides are the same. Let me just erase there and move this down. That actually makes the hexagon a series of equilateral triangles, right? So there we go. So these two sides here, okay, would actually be the same as the lengths of C, because these are all equilateral triangles. So with that in mind, then I could also go and say that the B to E vector would be double C, okay? And that's if I knew my geometry very well, which is something you should know. So 2C would be a multiple of that one as well. So there are two ways, like I said, that you could have labeled that vector. Okay, either by going from another path, following that path around, and saying B plus C minus A, or you could say that it equals to 2C. Now, let's go and have a look quickly at the next part of the question, because they also wanted the vector A to D, which goes across the other way. Now A to D from there would be A plus B plus C. It's parallel to B. So in this case, I'm also going to say that A to D could be 2 times B, or 2B. Alright, does that help you answer some of these questions? I'd like you to keep on going with this exercise. You should be able to go down to number 8 there and finish those. Now in the next section, they talk about the addition of the vectors like I showed you in the hexagon. Okay, and so let's just look at it in this quick perspective here. Okay, so if the vector A runs from O to P, and the vector B runs from O to R, then I can also say that P to Q is the same, because remember, this is a vector in the same direction, parallel, and also equal in length. That's a parallelogram. And so P to Q is also the vector B. But if I wanted to go from O to Q, then I could follow the path of O to P, which is A, and then also from P to Q, which is B. Okay, and so that I go A plus B, and that's what they've labeled OQ. It is A plus B. So this is what we call the addition of vectors. Okay, so there they've said that we define A plus B is equal to OQ, okay, as the diagonals starting from O. OQ is called a resultant of A and B. Okay, in other words, if A and B are put together, what results? Well, I'd get, if I put A and B together, I could go from O to Q. Okay, that's what I could do. That would be the result of going along A and then along B and following those two vectors. Now, I want to go and show you something in regards to this, okay, and I want to show you an interesting mathematical idea. If I asked you a question, what is 1 plus 1? Many of you would tell me that it is 2. But when it comes to vectors, this would not always be the truth. Because you see, if I had a vector that was 1 in length, and let's call that vector A, and then I moved another length A, and that vector is also 1, well, then I would be moving to A, yes? And then 1 plus 1 is 2. But what if I went 1, and then I went another vector 1 back? Okay, because the other vector is in the negative direction, okay, that 1 plus that 1 would mean that I am actually going 0, or I'm not going anywhere. I end up back where I started, because that would be A minus A, which is 0. Now the fact is, if I walked that path, I would have walked 2 times, okay? It's not that I'm walking 0, I'm walking 2, but my resultant is 0. I could also go from A and then to A, and that's 1 and 1, okay, but where do I end up? Well, that would be my resultant again, okay, and if I used Pythagoras, if this was 90-degree angle, then this length would be root 2. So now 1 plus 1 would make root 2. So 1 plus 1 could make any value actually somewhere between 0 and 2. Okay, 0 would be the minimum resultant from two vectors that are the same length, 1 and 1, and 2 would be the maximum resultant of two vectors that are 1 and 1. But I could get absolutely any value in between in the way I arrange those vectors. You see, that would be 1 and 1. That would be a small distance like that. And I could keep, like I say, increasing the angle until I got all the way to a 180-degree angle. They are in the same direction, and that would then make the 2. So the addition of vectors is a bit different to the addition of just normal scalar values. The direction plays a very big part in the calculation of the vector, okay, or the magnitude of the vector. Now we're going to play a little bit with that, but I'll continue with some of this into the next session. Okay, just that information for today. That should keep you going, and you should try and finish that exercise number 1. This is a little bit easier to start off with, and hopefully you'll be able to settle into the ideas of vectors quite quickly.